Hi class, Dr. Searcy here with the Chapter 2 lecture on the textbook. And the title of this chapter is Frequency Distributions. Basically what we're going to show you here is once you have obtained data, how do you go about organizing it so that you can summarize it? Let's start off thinking about an example of some data that we've collected. I've written an example here, and I'm calling it just simply sample data. And it's completely hypothetical data that I've made up, but you can just kind of think of what it might be. Let's think that maybe what's happened here is that a instructor has given some students a test, maybe a short quiz, and the maximum possible number of points on the quiz was 5. So what you have here is a collection of different students' scores on the quiz that each one took, right? So one student got a 5, another student got a 4, one got a 2, a 3, another student got a 4, and so on, right? So this is my sample data that I'm using as an example. By the way, let's remember, a sample is a group that you selected out of a population. But let's just kind of get into then, what do we mean with this term frequency distribution, right? And how do we use a frequency distribution to organize the data? Well, a couple things we can say about the frequency distribution is first that the purpose behind it is to provide an organized picture of the data, right? That's why we're creating a frequency distribution. But from there, we can also say that they show how many scores are in each category. Now, I do want to kind of explain these two important terms in this statement. First important term is scores, and the next important term is category. We have scores here, right? So that 5 is a score, 4 is a score, 2 is a score, so on. But we can also think that we've got categories of scores here as well. The categories of the scores are what was a possible score here? What was a score that someone could have gotten, right? And we're saying, oh, a person could have got a 5, or they could have got a 4, or a 3, or a 2, or a 1, right? So that's how we mean with the categories. The score is the actual score that the person got, that they actually got. And so it's important to have an understanding of the distinction between what a category is and what a score is, but I'll keep on explaining those as we move forward here. Let's go ahead and move on to the next point that I want to make. Here I'm saying that X's are scores, right? And we kind of talked about this in chapter 1 at the end, where I was going over the important symbols that you need to know. Remember that we said X's are the scores for the first variable. As it turns out, in the sample data that we're talking about, I've only got X's, right? I've only got one variable that I'm talking about, and it's the scores that the students got on the test, or on the quiz. But now I am introducing a new symbol that you need to know. That new symbol is the symbol F. When you see F's, think of them as the frequency of scores, or how often one category of score has occurred. For instance, if I were to say for the category of 4, the F, or the frequency, is 2. And the reason why we say the F for 4 is 2 is because if we look here and we ask how many people got a score of 4, we see the person here got one and a person there got one. And that's it. Just 2 people got a score of 4, right? So that's F for that. Another thing that we want to know is that when we create frequency distributions, they can be created either as tables or as graphs. And in this lecture, we're going to go over both types of frequency distribution. I'll just let you know, I'm going to spend some time talking exclusively about tables, and then I'll spend some time talking exclusively about graphs. So let's talk about tables first. What do I want to say about tables? First, I want to give you a sense of what a table looks like. I took this data and I created a table for it. And that is this table here. Okay, so what I did was, a table is basically a group of columns, right? And a column is a list of numbers that move in a vertical fashion. So I've got a column for X and I've got a column for F. Remember that X is the category of scores and F is how often each score occurred, right? So the way that this is organized is I'm saying that for the score of 5, there was one person that got a 5, and that was that one person right there. For the score of 4, there were 2 people who got 4s. We already pointed them out, that person there and that person there. For the score of 3, there were 3 3s, one there, and there. For the 2s, there were 3 2s. We got 1, 2, 3. And there was only one person that got a 1 on the quiz. Right, so this is what a table looks like. And the reason why we created it is because it gives us this organized picture of the data. Now we have a stronger sense, a stronger understanding of what happened with our data here. Right, for instance, we see that most of the scores that the students got were a 3 and a 2. The 2 scores that occurred the least was this 5 and this 1. So tables are useful to help us understand the data in that kind of way. But let's talk about another symbol that we said that you needed to know from chapter 1. And that was the lowercase n. Remember that lowercase n stands for sample size, or how many participants you had in your sample. Now, one way that we could figure that out is we could just easily count how many scores we have here. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means that there were 10 people in the sample, or we had an n of 10. Sometimes it's hard to count how many people you had in your sample by counting from here, though, right? Because you have like hundreds of people in your sample, and you don't want to spend a lot of time going 1, 2, 3, 4, counting that way. So an easier way to do it, if you want to figure out what your n is you can simply add up all the scores in your F column, and that will give you your n, right? So let's go ahead and count. We got 1 plus 2 is 3, plus 3 is 6, plus 3 is 9, plus 1 is 10, right? So that's one way that you could find your value of n for a sample of data that you've collected. But then there are other things that you want to be able to figure out from a table as well. For instance, another thing that you might want to figure out is sum of x, right? So the question that's being asked here is, remember, this is the Greek letter sigma, and it means sum of, and when you put it in front of a symbol, it's basically saying that you're supposed to sum up everything for that symbol. Now, what you might be thinking is that, sum of x means to take this x column and add everything up there, right? Because that's where my x's are. And that logic is not totally incorrect, but it's not totally right either. The reason why it's not totally right either is because the F part of the table is saying that for each score, you've got multiple occurrences of the scores. So really what you need to do is you need to add up every time you got one of these. Every time you got a 5, or every time you got a 4, or every time you got a 3, and so on. So the way that you would do it is you would create this third column on your table that I'm referring to as x times f. Right? So I'm taking, in this column, I'm taking each individual x column and I'm multiplying it by its corresponding f value. That's how I've got 5 here. Here we're saying 4 times 2 is 8, 3 times 3 is 9, 2 times 3 is 6, 1 times 1 is 1. So now what I've done here is I've created a column of f values, a column of x values, but those x values are reflecting how many times each x occurred. And so now I can add this column up to get my sum of x, which ends up being 29. Let's see if I added up that correctly. 13 plus 9 is 22, plus 7 is 29. So yes, we got that right. Okay, but now we don't just use tables to find n or sum of x. We also use tables to find other information as well. For instance, what if I asked you to find the value for the sum of x squared? Now what you would have to do if you were asked to get this, you'd have to first recognize that what you're being asked to do is take each individual x value and square it. And to do that, you'd have to create yet another column of data and call it x squared. What are the numbers in my x squared column? They're basically exactly what this is saying. I've taken each of my x values and I've squared each one. So for instance, my 5 squared is 25. Why? Because 5 times 5 equals 25. 4 times 4 equals 16. 3 times 3 equals 9. 2 times 2 equals 4. And 1 times 1 equals 1. From there, now what I need to do is, we're still talking about the sum of the x's, so I still need to figure out what are the corresponding, how does the corresponding f values correspond to those. And so I have to take, to figure out sum of x squared, I have to take my each individual x squared values and multiply them by f now, or by their corresponding f value. So when I do that, I've said here, 25 times 1 equals 25. 16 times 2 equals 32. 9 times 3 equals 27. 4 times 3 equals 12. And 1 times 1 equals 1. Once I've gotten this column now, though, I can add them up. And I can say, okay, sum of x squared is 97. From there, though, I do have one other value that I can use my tables to figure out. And that other value that we have here is this notation. Now, remember, this looks like this, except we've got these parentheses around the sum of x. So remember, what this is telling you to do is it's telling you to take whatever your sum of x value is, and to whatever that number is, and to square it. Luckily, we've already figured out what the sum of x was. It was that 29 over here. So what this is commanding us to do then is to say, okay, take the 29 and multiply it by itself, right? That's the square. And once we do that, we have a sum of sum of x in parentheses squared of 841. Okay, so I think that you're going to come across some of these kinds of problems in the work in the book on your odds and evens problems. So here are some explanations of how to solve for each of those symbols. Now what we want to do, though, is we're still talking about tables, but now we're talking about a different way that we want to express values on the tables, and that is by expressing parts of the whole. Basically, what we're talking about here is when we analyze data, we often ask ourselves questions like, of everybody in the group, who got a certain score? Who got a specific score? For instance, who in the group got a 5? or who in the group got a 4, or who got a 3. That's what we're talking about when we talk about expressing parts of the whole, right? You have a whole group, and we want to know what did a part of the group get, or how much of the group got a specific part. Okay, so when we go to talk about that, then we use two terms called proportion and percent. And really what you need to know with these is that both of these are talking about different parts of the whole, and that there's a formula associated with each, and there's a specific way that we articulate each. First, let's say that we've got a set of data. And it looks like it's the same set of data that I have up here. Okay, so you got your 5, 4, 3, 2, 1 in your X column, and then you've got all of your different frequencies for each. Remember, the question that we have here is, say like, how many people in the group, or what part of the group got a score of 5, or what part of the group got a score of 4. If we want to express it in terms of proportion, the mathematical formula that we would use, we would say that proportion, or P, can be found by taking F and dividing it by N. Now, in this particular example, remember that the F values are each individual value in the column. And we've already figured out what N was. N was that 10 over here. So what we would do is, remember, we're asking what part of the group got a 5? To answer that question, we would just do this simple calculation where we're saying one person in the group got a 5, that's the F, and so we would take that and put it over N, which is 10, and that would result in the answer of 0.1 or 1/10. Right, so then we could say, oh, a 10th of the group got a score of 5. And then so on for all of the other scores as well. Right, we want to ask, well, what proportion got a 4? We go and do the math, we put F over 10, and we say that 2/10 of the group got a score of 4. And so on with the score of 3. There was a frequency of 3 for the score of 3, so it's 3 over 10, and so then we say 3/10 got a score of 3. Again, for the score of 2, there were 3 people who got 2, so we say that the proportion that got 2 is another 3/10. And then finally, for that one person that got a 1, their frequency was a 1, the N was a 10, and so we say that a 10th of the group got a 1. Okay, so that's how we express things in terms of proportion, but we often also want to be able to express these parts of the wholes in terms of percent. Basically, in order to calculate percent, we first have to know what proportion is, right? Remember, so for each individual row, we have a specific proportion that we're talking about. All we would do with percent is we would take that proportion that we've calculated and multiply it by 100. So for instance, I could ask, what percent of the group got a score of 5? The answer to that would be 10%, right? So a 10th got a score of 5. A 10th times 100 is 10, so then we say 10%. Same thing with all the other numbers, right? So 2/10 got a score of 4, so then 20% got a score of 4. 3/10 got a 3 and a 2, so 30% got a 3 and 30% got a 2. Again, a 10th got a score of 1, so 10% of the group got a score of 1. Okay, so that's everything I want to say about proportion, percent, and I believe even everything I wanted to say about tables, at least where we're looking at one score in the X column. Now what I want to do is keep on talking about tables. We're going to talk about a slightly modified version of a table. A modified version that we refer to as a grouped frequency distribution table. Right? So it's still a table that we're talking about, but now we're talking about organizing the data in terms of groups. Let me give you an example of how this might work. Let's see here. A couple of years ago, when I was teaching a research methods class, I asked the students in the class to give me some data. And this was the data that they gave me, right? So these are scores that I got from individual students. Let's count how many students were in this group. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So 11 students gave me scores. And I'll just tell you the question that I asked them, where they gave me these numbers. The question that I asked everybody in the class was, tell me how many social media friends do you have? Right? So this is like, how many friends do you have on Facebook? Maybe like, even think like, how many followers do you have, say, like on Twitter? So these are the scores or the answers that I got from the different students. 2 of the students told me 0. And what they're saying there is this student and this student said, I don't have any social media friends. Which is kind of hard to believe in this day and age, but I guess it's true. By the way, when I asked them these questions, I also asked them to give me their gender, right, their sex. And what I found from that was, of the students in the class, one of the zeros was a male student and the other 0 was a female student. Later, I presented this data to the class, and I told the class, hey, for those 2 zeros out there, one of you is a man, one of you is a woman. Maybe you guys should think about getting together. And when I did, everyone looked around to see who the 2 zeros were. But anyway, look at another interesting score that you see here. Another interesting score that really stands out to me, at least, is this 2,300, right? So that's one student telling me that they have 2,300 social media friends. By the way, on that, I got a quick question for you. What do you think this person was? Was that a male student or a female student? And I just want you to ask me, just give me your gut reaction. Do you think that's a guy or that's a girl? Do you think that's a guy or do you think that's is that a gentleman or is that a lady? Well, the answer is that was a score provided by a lady, a female student. And it kind of confirms a theory that I've got. And just that theory is that if you make a comparison of male social media users to female social media users, I think that the female social media users are more likely to have more friends than the male social media users. Wonder if that's true in general. It's at least true in this sample, which I thought was kind of interesting. Okay, but getting back to the point, we're talking about grouped frequency distribution tables. What I did with this set of data was I made it more easy to read by putting it into a grouped frequency table. All I did was, instead of keeping like my X column values like this, I created categories of X values. And that's this column here. Right? So I said, this row is going to represent anybody that got a score between 0 and 299, right? 0 friends to 299 friends. Here, 300 friends to 599 friends. And then from there, I created that other column, the F column, right? Remember, this is that frequency column. And so now with this, what we're seeing is how many people in this group got a score of between 0 and 299. Now, according to this, what I should be able to find, according to this, is that there are 4 scores in here that are between 0 and 299. Let's see if I can find them. Got one here, got one there, there. Where's my 4th person? And I've got one here, right? So There are my 4 people in that first category. One person got 200, 136, and then the 2 zeros. And then you can see how it's organized for the rest of the way down. Now I'll just say that the reason why a researcher would want to organize their data in terms of a grouped frequency distribution table is maybe they've got a lot of scores that they have to account for. Too many scores to show on a single table like this. That's why they would create these categories of X values. Okay, so a couple of additional things that we want to say with this is that group frequency distribution tables are used to present groups of scores instead of individual scores, right? So this column is not part of the group frequency distribution table. The group frequency distribution table just consists of that part. Okay, in addition to that, groups are called intervals, right? So what do we mean by group? Each of these X categories is a group. And we also think of it as an interval as well, right? So the size of this interval is from 300 to 599. Another thing that we could say is that when you create a group frequency distribution table, let's say here I do mean 10 intervals is desired, but what I really mean is a max of 10 intervals is desired. You don't want to have more than 10 intervals in your group or in your table. Otherwise, it doesn't look as organized as it should. It's not presenting the data as efficiently as it ought to, right? You're doing it this way so that you have this easy to see idea of what's going on with your data. Here I easily see, oh, there were 4 people that had a low score. There was only 1 person that had a really high score, right? And so when you have more than 10 rows or 10 intervals, then it gets harder to see that. It's not as efficient. Another point that I'm making is that the interval size should be simple. What do I mean by the interval size? I mean how big each interval is. Basically, I've spaced them out here so that they are, each interval is 300 big, right? Or 300 friends big. Another point that I'm making is that all of the intervals have to be the same width. So whereas I made this interval have a size of 300, all the other intervals have to have a size of 300 as well. They have to be equal in size. Okay, let's see. Beyond that, that's everything I wanted to say now about tables. So I've just introduced to you tables and then also grouped tables. Now, sticking with this idea of talking about frequency distributions, we're going to talk about the other kind of frequency distribution, the graph. Before we get into the graph, though, I need to take a moment to do a bit of review from chapter 1. Right, and this will help you understand everything I'm going to say about graphs in a moment. The review that we need to do is on the topic of scales of measurement. Right, so this is one of the last things that I talked about in chapter 1. And I said that there were 4 different ways that you're going to organize the data when you design a study. And so I just want to remind you of what those 4 different ways were. First, remember that we identified them using the acronym NOIR. Right, so there were 4 different ways. One started with an N, an O, an I, and an R. Let's see if we remember what these 4 different ways were called. The first one was the nominal scale, or the nominal way of organizing the data. Remember that nominal was where you just created categories of data, and the way that you organized them was by name, right? So you had a name of a certain category and then a name for another category. An example, I don't know if I used examples last time, but an example that we could think of is like you go out and you ask people to tell you what their favorite cereal is. And when you come back to analyze your data, you find that there were three major categories of cereal that people liked. Either like Lucky Charms, which I think is my favorite, or Cheerios, or Fruit Loops, right? Each one of those is a category, and you would just see, well, how many people told me Lucky Charms, how many people told me Fruit Loops, or how many people told me was the Cheerios. Okay, so that's nominal data. Remember that the second category is ordinal data. And ordinal is where you're still talking about categories, but now you're talking about ordered categories. Say, for instance, first, second, or third, right? So you go out and you ask people, hey, did you take a race? Did you run a race last week? Oh, yeah? What place did you come in? Oh, I came in first, right? Or I came in second, or I came in third. When you look at it that way, then we're talking about ordered categories. We call that ordinal data. Okay, the third category is the interval category. Now remember what this is this is ordered categories, but where there is no zero. Right, an example of this was like the Likert scale. Likert scale was like that depression scale that we talked about, where someone could tell you how depressed they are on a scale of 1 to 10. That would be an interval scale. Then the fourth scale was an interval scale, but with zero, right? And that's called ratio. Remember with the ratio, if you do have a zero, the zero is referring to the absence of something, right? And an example of this was money. You could go up to people and you can ask them, how much money do you have in your wallet right now? Some people would say $1. Other people would say like maybe $3 or $4. But you could also get an answer of zero, no dollars. If that happens, then you would put your data on the ratio scale. Okay. Why I am going over this review will become clear in a moment. So I'm just going to steer into talking about the different kinds of histograms, the different types of graphs that we can come up with. Right? And the first type of graph is a graph referred to as the histogram. So how do I want to do this? First, let's just kind of describe what a histogram is. Here we'll say that it's used for interval or ratio data. Right, so this is why we just did that review. So you're going to use a histogram if you have data that fits into these two categories, either interval data or ratio data. From here, let's go ahead and take a look at the graphs that I have as examples. Okay, so I have two example graphs to show you here. Let's talk about this blue-looking graph first. Right, so this is a histogram. The way it's working is you've got two axes. You've got what's referred to as an axis here and an axis here. And I want to describe what how those two axes are expressing or articulating the data. Let's say that you've got this first axis that I'm referring to as the vertical axis. And that's this axis here, right? Vertical means up and down. This is the axis that's going up and down. That axis, no matter what graph, what histogram you're always talking about, that axis is always going to show your F information. Right? Remember, F is how often something occurred. So let's look at it here. Here you got F, standing for frequency. You got 1, 2, 3, and 4. And basically what's happening is you've got these bars over these numbers, and the bar is telling you what number or what frequency happened for that bar. Okay, so let's look at then what the bar is showing, or what's going on your... I'm sorry, before we do that, I have to make this last point. When we talk about these vertical axes that are always showing frequency, we also always refer to those axes as the y-axis, right? So you got a y-axis there on this histogram, and you've got a y-axis here on this histogram. Okay, but now let's explain the other axis, what we refer to as the horizontal axis, right? And that's the one that goes side to side on the bottom of the histogram. This axis is always going to list your x values, right? And we call that axis the x-axis, right? So the x-axis, the x-axis. So let's take a look at how it's showing the x values on this graph. Here you've got a frequency distribution table that is corresponding to this histogram. You've got your x values here, and those x values are being shown on the bottom of your x-axis. It also is showing your f values, right? The frequency of how often a 5 occurred, a 4 occurred, a 3, and so on. And so that's what these numbers represent. And so what you're seeing here is, according to my table, for the score of 1, I only got one person that got a 1. That's what we're seeing here. My x score of 1, and only one person got a 1. Here, when I look at my x score of 2, I'm seeing that 2 people got a 2. And that's what this bar is saying as well. And then so on for all the different bars. Let's take a look, though, at my other histogram as well. This histogram is a histogram showing this data, right? And so it's working the same exact way. My y-axis is showing my frequency. My x-axis is showing my x categories. And it's even showing the way that I've got them listed in groups here. I don't know if you guys can see this, but like my labels on my x-axis, for instance, this label is saying less than 300. Less than 300 is another way of saying 0 to 299. My table says that there were 4 people that got less than 300, and so that's why my bar comes up to the 4 on the y-axis. Okay, one thing I need to point out about histograms that's really important is that the bars touch. Just something that you always want to keep an eye out for. When you're looking at graphs, when you're looking at whether it's something a histogram or not, you know that you're looking at a histogram if, as you're looking at this graph, the bars are touching, right? This bar is touching that bar, and then this one's touching that one. Same thing over here. They're not going to touch if there's no data between the bars, right? For instance, here we've got this category of less than 1,200, but there's no bar there. Why is there no bar there? Because there were zero people that got something in that category. So for that reason, there's not going to be a bar there. But if you did have some people in that category, there would be a bar, and that bar would be touching its neighbors. Okay, so very important point that you want to remember in histograms, the bars always touch each other. Another point that I need to make is that one thing that researchers like to do with their data when they've come up with a histogram is they like to draw a line that hugs the bars to kind of see if there's a pattern that the bars are making. For instance, here, when I draw my line, it would look something like this. Right? And that is telling me something about the data. Say how this line looks as opposed to this line. Researchers like to draw these lines because the curve of the line gives the researcher information about what the data is doing. And so that's what I want to talk about next here. And that's where we're going now to this topic called histogram curves. Right, so first of all, a curve is that line that you can draw over the data. The reason why you want to do it is because you want to see what shape that line or that curve is taking. As it turns out, there are basically 3 different shapes that you can get with those curves. I want to go over what those three different shapes are, beginning with the first shape, the shape called the smooth curve. Okay, so what we have here is a curve that looks to me like a bell, right? So like maybe like here's the handle of the bell, and like you got the little ringer thingy right there, and you like can shake it, and it's a bell. The reason why we call this a bell, or the reason why this is also called a smooth curve, is because we generally think that the average score, right, the middle of the distribution, is right in the middle of the curve. And that actually is the case here, right? So the average is often very close to the score that's seen most frequently. In this distribution table, you had more threes than any other score, right? And that usually corresponds to the average score as well. So if you can do that with your data, right, say like draw a line right through the middle, and you see that once you've done that, you've got an equal amount of the curve on the left side of the line as you do on the right side of the line, then that tells you that you have this type of curve called a smooth curve. And another point that we're making with this is that this is the type of curve that the researcher wants to find. It's their desired curve. The reason why is there's this theory that says that if I were to go to any population, right, some group that I'm interested in studying, and I were able to ask everybody in that population a question and get an answer from them, when I collected their answers should look like this smooth curve. The way you want to kind of think of it is what you're doing is you're building a pile of answers here. And it's almost like you've got this hose and you're just letting stuff out of the hose, right? And as stuff falls onto the pile, as the pile grows and grows and grows, the pile gets bigger in the middle where the stuff is falling on. That is like a natural occurrence that happens, right? Maybe if you want to test this, you can go out and rake your leaves in your backyard and build a pile out of them and just throw leaves on top of the pile and see what type of shape does your pile end up becoming. I will venture to say that that pile will resemble a smooth curve. Now you should also know that this curve goes by other names as well. It's also often referred to as a bell curve. And the reason why it's referred to as a bell curve is because, how I explained it kind of looks like a bell to begin with. But many researchers will also refer to it as a normal curve. The reason why they'll call it a normal curve is because that's what data should do if it's normal, if it's accurate data. Then it should, as it gets piled onto each other, it should produce this shape. Okay, but then there are two other types of curves that researchers can find as well. Another shape of a curve that they can find is one that they may refer to as positively skewed. First, let's note that this type of curve is not desired. The researcher does not want their data to look like this. Okay, and so let's kind of look at some data where we would find this type of curve where it's positively skewed. As it turns out, that's what I have here. I have a positive skew with my data from my social media friends question. And what this is suggesting is that most of the data is clustered in a specific part of the curve, right? It's mostly clustered over here. Sure, you got a few answers here and a few answers here, but most of it is over here. And so that's why you have this shape like this. Okay, a reason why you don't want this is because when you go to analyze it, it violates this idea that the data that you're supposed to be getting in would look like this, right? So it's suggesting that maybe there's something off about this group that you're studying, and you should go get maybe more people to throw into the group, or consider how you're asking the question. It does cause me to wonder why I got the data that I got here, right? So I have this class of college-age students, and most of them are telling me that they've got a small number of friends compared to a few people who have a larger number of friends. Maybe one reason why it's skewed is because where you like, for it to not be skewed, you'd have to have people over here, like on the other side of the zero, and it's impossible to have negative friends. Wow. It's possible. It's impossible to have less than 0 friends. I guess you can have negative friends, but you can't have less than 0 friends. Okay, so that's a positive skew. But then the third type of skew, or type of curve that you can get, is one that is negatively skewed. And this type of curve is also not desired. By the way, you may be asking yourself, why the names? Why is this curve called positive and why is this curve called negative? The answer to that is you want to think about the tails of the curves. Right, so what's a tail of a curve? A tail is that part that is moving away from the hump. Right, so let's say that this is the hump of the curve here and the hump of the curve here. The tail is the opposite end of the curve. And this is where we look at to figure out whether we have a positive skew or a negative skew. Basically what's happening is in the positive skew, the tail is pointing towards the positive direction of, like, say, the number scale, right? If we had a 0 and then we had our numbers to the right of the 0 and your numbers to the left of the 0, the numbers to the left would be your negative numbers. The numbers to the right would be your positive numbers. So in a tail, or in a curve like this, where the tail is pointing in the positive direction, then you call that curve positively skewed. On the other hand, if your tail is pointing in the negative number direction, then you have a negative skew. Okay, so that's everything I want to say about histograms. By the way, maybe one last parting comment I'll make on this section. As far as how you're going to present data, how you're going to analyze data, in this class, we are going to use histograms a lot. And so you really want to have a solid understanding of how these graphs work. Understanding these graphs will help you to understand how to do the problems in future chapters, because it'll be based on what you see with the graphs. So you really want to understand this stuff that I've just told you. Let's go ahead and move on now to another type of graph that we can talk about, and that is the bar graph. First, we'll say that these graphs are used for nominal and ordinal data, right? So these are the two scales of measurement where you were talking about the categories, right? So this is that first one where you're talking about, like, the names of the categories, like the different cereals, the tricks, the Lucky Charms, the Cocoa Puffs. I think I'm coming up with new names now. And then this was the other category, but now we're at the ordered categories, like the first, second, or third. So you're going to use bar graphs with these kinds of data. What do I want to say about this? you still have a y-axis and you still have an x-axis. And each axis is still doing the same job that it did for the histograms. Y is still listing F, and X is still listing your X categories. One other thing that we want to know is that there are also gaps between the bars in the graphs. So let's just take a look at a couple of graphs that we have here. So each one of these is a bar graph. The top one is showing how some nominal data can be presented, right? So a researcher did some measurements on different individuals and looked to see if they could identify different personality types in the different individuals. I'm sure you've heard of that A-type personality. That's supposed to be like a person who's like really assertive. And then there's the someone who's less assertive, the B or the beta type personality. Apparently there's this third category personality as well. I think this one is supposed to be like the beta that recognizes that they're a beta, but then they outsmart the alpha. I think that's what this person is. And it's interesting to see that if that's the case, that there are more of this category than even the alphas. I thought that this category might be the minority. But anyway, one thing I'd ask you guys to recognize with this is try to figure out, is this category, we know now that it's a bar graph, so it's got to be either nominal data or ordinal data. Which of the two is it? Is it nominal or is it ordinal? I'm going to say that this is a presentation of nominal data. And the reason why it's a presentation of nominal is because there really is no fixed order to the different categories. There isn't like a first, second, or a third here, right? It's just the different names. Same thing with this other category, or this other bar graph, right? So here, someone went out and they asked people to tell them their different favorite pizza toppings. So some people said, I just like cheese, I like mushrooms and olives, I like sausage, and I like pepperoni, right? So again, here are our X's, or our different categories, and that's our X-axis. And then on the Y-axis, you've got the frequency, how often each category was supported. And what we're seeing here is that more people liked the pepperoni than the other categories. So again, this is a nominal bar graph. I guess I would like to just kind of show you what might be a ordinal bar graph. So like, instead of like having personality type here in this A, B, and C, we say that what we've done is we've gone out and we've asked people who ran a race, right? If you've run a race in your life, what was the place that you came in the last race that you ran, right? And so we could have people say, in the last race that I ran, I came in first, or I came in second, or I came in third. Right, that would be an interesting question to go out and ask people. May reveal something about their personality. How are people who say that they came in first in the last race that they ran? How are their personalities different from, say, someone who says that they came in third in the last race that they ran? I wonder if there would be any interesting personality distinctions in these individuals. But let's go ahead and move on to talk about other types of frequency distributions. So far, we've talked about presenting data on frequency distributions in terms of tables. There was where you could just present the single X values or the grouped X values. We've also talked about presenting them in terms of graphs. And with graphs, we've talked about histograms and now bar graphs. Now, I just want to talk about one last way that you can present data, and that's by using the stem and leaf display. Now, I should warn you, if you are a marijuana user, there's no reason to be getting excited right now. Stem and leaf display is simply another way to present data, to organize it so that it can be summarized easily. Okay, but let's talk about what we do with this. So let's say that a researcher has come up with some data, and now they want to organize that data, right? And let's say that this is the data set that they've created. They take that data set and they create this stem and leaf display, right? And really what you want to see here is that you've got two groups of numbers. You've got a group of numbers here and a group of numbers there. As it turns out, the first group is your stem, right? So that's your stem in this first column of numbers. The leaf, on the other hand, is the second column of numbers. So what are each of these columns doing? Well, let's say that for the stem, what you've done is you've gone through your data, and in your stem, you've just written down the first digit of each number that you see in your data. So for instance, we've got this 3 here. That 3 is there because it's saying that there is a 3 in a tens place in here somewhere. So then the leaf is the last digit of each number. And so the way that this reads is, like say for instance, this 3 with the 2 and the 3 is it's saying, in the set of data, I've got a 32 lurking around out there somewhere. Let's see if we can find, here it is, the 32. But it's also saying that you've got another number in the 30s category, and it is a 33. Let's see if we find that 33 anywhere in here. There it is, right there. Okay, so then just to make sure that you're getting this, the logic continues. Now, in the stem, we've got a 4. So that's saying in the tens place in here, I've got a number that starts with a 4. And then there are going to be 2 numbers in the 40s in this data. I should be able to find a 42, and I should be able to find a 46. Where is the 42? Oh, I see the 42. I'm going to put a box around it. Right, so that 42 is corresponding to the 4 and then the 2. But it's also saying that I've got a 46 as well. Oh, and there it is right there. Right, so on and so forth with the other numbers as well. I'll go ahead and let you have the fun of trying to find the other numbers, and I will discontinue the lecture at this point. Thank you very much.